Welcome back to the Dr. Liu VCE Physics channel. In this video, we'll go through the 2018 VCE Physics exam, focusing on questions related to light as a particle. My explanations may not be perfect, so if any teachers, parents, or students notice any errors, please feel free to offer your feedback. When a beam of particles, such as electrons, passes through a narrow slit, the particles diffract. According to Heisenberg's uncertainty principle, precisely defining the particle's position by forcing it through the narrow slit introduces a greater uncertainty in its momentum. This increase in momentum uncertainty means the particles are more likely to have a significant sideways velocity component, causing them to spread out and change direction after exiting the slit. The maximum kinetic energy of a photoelectron has a linear relationship with the frequency of the incident light, with the slope of the line equal to Planck's constant. The y-intercept of this graph represents the negative of the work function, and a higher work function corresponds to a higher cutoff frequency, which is the minimum frequency of light needed to eject an electron. To investigate the photoelectric effect, Tsai and Kim set up an experiment. With the light source on and a filter in place, Tsai and Kim measure the maximum kinetic energy of emitted photoelectrons by gradually changing the collector voltage until the current measured by the ammeter just falls to zero. They record this voltage, the stopping voltage, for each frequency of the incident light and plot their results in a graph of stopping voltage, Vs, versus frequency of the incident light, as shown below. With 600 THz light, the ammeter always shows zero. Tsai wants to repeat the experiment for this frequency with a much brighter light source and wants to expose the metal to the light for much longer. Kim says photoelectrons will never be ejected with this frequency of light. Kim is correct. The frequency of the light, 600 THz, is lower than the cutoff frequency, 700 THz. The photoelectric effect only occurs when the frequency of the light is at or above the cutoff frequency, regardless of the brightness of the light source or the duration of the light shining on the metal. The wave model of light supports Tsai's idea. According to this classical theory, light's energy is determined by its intensity, or amplitude, not its frequency. It also assumes that energy is delivered continuously. Therefore, a brighter light, or a longer exposure time, would provide enough cumulative energy for the metal to absorb and eventually eject electrons, even if the light's frequency is below the cutoff. You can find the value of Planck's constant from your graph by following a few steps. First, draw a line of best fit for your data points. Then, calculate the slope of this line by dividing the rise change in voltage by the run change in frequency. This slope is not Planck's constant itself, it's the constant divided by the elementary charge, h.e. So, to get the final value for Planck's constant, simply multiply the slope you calculated by the value of the elementary charge. The work function is the minimum energy required to remove an electron from a solid surface. On a graph of stopping voltage versus frequency, the y-intercept is the negative of the work function divided by the elementary charge. A line of best fit can be drawn and extended to the y-axis to find this value. For example, if the y-intercept is minus 3.5 v, the work function is 3.5 eV, a value that should fall within the accepted range of plus or minus 0.5 v. Alternatively, the work function can be calculated by multiplying the cutoff frequency by Planck's constant. The diffraction patterns for X-rays and electrons through thin polycrystalline aluminum foil have been combined in the diagram in Figure 18, which shows an electron diffraction pattern on the left and an X-ray diffraction pattern on the right. The images are to the same scale. The X-rays have a photon energy of 8,000 eV. When the diffraction patterns produced by two different particles are identical, it means they have the same wavelength. Given that the X-rays have a photon energy of 8,000 eV, their wavelength can be calculated. To do this, we use the relationship between photon energy, Planck's constant, and wavelength, where c is the speed of light. Since the X-ray is a form of electromagnetic radiation, its speed is indeed c. Therefore, the calculated wavelength for the X-ray will also be the wavelength of the electron. The kinetic energy of the electron is calculated in two sequential steps. First, because the electron's wavelength is known from the diffraction experiment, we can use the de Broglie equation to find its velocity. The de Broglie equation relates a particle's wavelength to its momentum. Once the velocity is determined, the electron's kinetic energy can be calculated using the standard kinetic energy equation. The wavelength of visible light ranges from approximately 380 to 750 nanometers, corresponding to a progression of colors from violet to red. The shortest wavelengths are perceived as violet light, 380 to 436 nanometers, followed by blue, 436 to 495 nanometers, green, 495 to 566 nanometers, yellow 566 to 589 nanometers, and orange 589 to 627 nanometers, with red light occupying the longest wavelengths, 627 to 780 nanometers. The discrete spectral lines of a hydrogen lamp are a direct result of electron transitions between fixed energy levels. Electrons in an excited state emit photons as they fall from a higher to a lower energy level. Because the energy levels are discrete, the energy difference between them is also discrete. This means that the energy of the emitted photons is quantized, resulting in discrete frequencies and wavelengths that appear as distinct lines in the spectrum. This exam section focuses on the quantum model of light and matter. It is worth a total of 18 marks, contributing 13.8% to the final grade of 130 marks. Multiple choice questions, 2 marks. Question 15. You'll need to explain the phenomenon of diffraction using Heisenberg's uncertainty principle. Question 17. This question tests your understanding of the photoelectric effect. It asks you to explain why the lines for different metals are parallel and why a higher work function corresponds to a higher cutoff frequency. Short answer questions, 16 marks. Question 17. This question requires you to describe the particle model of the photoelectric effect. You will also need to use a graph to determine Planck's constant and the work function. Question 18. You must explain how electrons behave as de Broglie waves. You will then need to calculate the electron's de Broglie wavelength and its kinetic energy. Question 19. This question asks you to explain why the emitted spectrum of a light source, such as a hydrogen lamp, is composed of discrete lines and how this observation supports the idea that energy levels are quantized. Should you require assistance, please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE physics, chemistry, and biology channels.